Hello, everyone, and welcome to a discussion on cross-validation in advanced machine learning. This is Module 6. We'll also talk about Deliverable 7. So, should be a fun time. Jumping straight in. In this module, you're going to learn about the concept of it's a mixture of terminology here, and frankly, it's a little concerning. But at the same time, the key thing here is about cross validation. That's the central point of the discussion. This is certainly not new. We've talked about this in numerous courses, but the basic idea is the way to validate models, explain why we do it, explain the technologies, the approaches, and then also be able to apply it to a real data set. This is a little bit confusing because of the term cross-learning may also be confused with the concept of transfer learning, which would be quite applicable for a course in advanced machine learning. Transfer learning is whenever you take a model, especially typically a connectionist model, so something with neural networks in it. You train it in one domain on a certain set of data. You then make some modifications to it and then use it with maybe a little bit of additional training in some other domain. So that ideally you're reducing the amount of time you have to spend training it. So that's one of the concepts that's a little confusing. The terminology is not the great there, but for the purposes of this conversation, we'll talk about model validation, and in particular the approach that we typically use to do it. The thing that you're trying to address here is you don't want your model just to do really well on the stuff it's seen before. So instead, the way you do that is you keep a certain amount of the data held back so that you can validate it and test the model and determine the accuracy on unseen data. So you can get a sense of how well your model is going to generalize once you deploy it to the real world. So the basic idea is that you do this concept of a holdout. The size of that holdout depends upon the quantity of data, the specifics of a particular environment, but the intent is to hold out enough information so that you can determine with a certain degree of confidence how well it's going to do when it sees something it's never seen before. Because you wouldn't want something to do exceptionally well on the stuff that you trained it on and very poorly on the things that it's never seen before. So generalization is a really important concept, and that's what we're talking about here. And part of the problem here is around over and underfitting, and that's what we're trying to avoid. Overfitting or underfitting is that you either go too close to the data that you have so that you're actually losing the ability to generalize, or you don't get close enough. So think of it as you've got some points in a simplistic world of two dimensions, and you're trying to get a line to go through all those points. One approach might be to make it to where you literally hit every single point. The problem with that is there may be something going on outside of that to where you do really well on your training, but you do very poorly on your holdout or your test set. So the concept of the distinction between the test set and the holdout set is also sometimes called a validation set, or it's used during the process typically of training so that you can determine how it's going, basically how good is your training moving through, and how well do you think you might do when you actually deploy in a real world scenario. So the way that we typically do this is the typical test train split. So the idea is that you take your label data set typically, because this is typically what you're using it for. It's the whole point, right? Because you know the answer. You want to see how close you get to the actual answer when you're doing your predictions. So you take that, you hold out a portion of it, maybe 20%, maybe 1%. If you've got zillions and zillions of labeled data to work from, you may have a relatively small amount of holdout and test set. If you've got a relatively small amount of data, you likely will go with the typical 80-20 split, with 20% being held out of that 80 for your validation and being referred to as the holdout set. So your basic idea is you take your data set, randomly split it into essentially three data sets, The training set is what you use to do, go figure, your training. It is what you tell the algorithm, hey, adapt yourself such that you fit this as well as you can. And also, there's some kind of rules of thumb that are pretty important. You want to ensure that your data sets are all coming from the same distribution. That means that you want to do something to ensure that you're not getting biased data. One approach is to do some random sorting or random selection. Another approach might be to actually go and do some stuff with stratification. But the key thing is that you want it to be representative, right? So that you don't have bias in either of the sets. You certainly wouldn't want a bias in your training set. You wouldn't want a bias in any of your test sets. So that's the key concept. You also want to make sure that you may end up getting a relatively small amount, percentage-wise, of your data being used for the test and holdout. So, and your friend is the test train split function, which is in the scikit-learn library. It is the thing that you will probably find yourself using most of the time. I know I do. Another approach that you may want to use, depending upon especially situations with small amounts of data, is your k-fold sort of approach, where you have your bucket of data that you're picking to be the test set for one sort of iteration. Then you switch over to the next bucket over for the next iteration, and so on. So you can see the four different runs, starting with iteration 0 through 3. The first 20 are the test set. The second 20 are in the second iteration, so iteration 1, and so on. That's the idea here is to basically try to avoid overfitting, and yet at the same time address problems where you simply don't have enough data. It's very typical when you're doing any kind of labeled data set sort of operations that you spend a lot of time, money, and effort trying to get your labeled set as good as it can be. And that may mean doing hand inspection, labeling, maybe outsourcing it and having some firm do that for you. And frankly, it becomes kind of the limiting factor on a lot of these algorithms because your data needs to be as good as possible, especially whenever you're dealing with well, all of it does, because so if you do your emphasis on your training set and say, hey, the training set's got to be perfect, but you have a flawed test set, then you're going to have cases where your algorithm might have actually got it right and you don't think it does because your test sets may be incorrect, so you may be mislabeled, and so on. So those are things where you want to spend as much time as possible making sure that your data is clean. And you may even want to consider, if it's problematic to come up with labeled data, trying some other approach, maybe reinforcement learning or some sort of ensemble approach where you find some other way to determine what good looks like. So rather than having something be labeled, perhaps you have some sort of a value so that you can maximize that value or minimize that value. So you determine how close the thing is getting to what you really want it to be without it being explicitly labeled. And so those are part of the reason why those sort of approaches are in existence, is because it is such a pain to get your data labeled. It is a lot of effort, a lot of cost, and if it's incorrect, and especially if you don't know how poor it is, then it is a real problem. As I've stated before, if your data is only, say, 80% correct, meaning that it's mislabeled 20% of the time, the best you could ever hope for is 80% of your algorithm. Likely it's going to be something much lower than that because of the nature of how that stuff works. So you want to make sure you get your data as pristine as possible. So again, another look at the k-folds cross-validation approach. And it's a fairly straightforward sort of approach, and you do it with neural networks as well as other types of training. And you basically split your data into k groups, k being just an integer. Then one of the groups is held out to be used as your test set, and then the remaining groups are used for your training. You may also, within that training set, take a certain percentage and hold out for your validation set as you're going through the various training epochs and whatnot. And so an example of a four-fold cross-validation approach has four groups, and you can see it on kind of the right side there. And during the first split, fold one is held back as your test set. Then in the second split, fold two, and so on. So that's the basic idea of trying to. It's not quite fabricating data, but it's getting kind of close. So in order to evaluate how well something is doing, you have to ensure that the neural network or whatever model you're using hasn't seen the data before. If it's seen the data before, then it's highly likely that you're going to be thinking it's doing better than it is. And so you might have overfit the model so that you do great whenever it's seeing what it's seen before, because it should, right? Something is kind of off if a model doesn't do very good against the data it's already seen. That indicates that probably it's undertrained or underfitted. So, but at the same time, you don't want it to be perfect either, because you're potentially giving up general ability of the model for something that really, in the end of the day, doesn't matter too much, which is how well the model does against the test data or the training data. It should do really well. That's to be expected, but it's not going to see that data again when you're running it in a real world scenario. So a good idea is to keep your data as simple as possible, to the point that it is sufficient. There's this concept of the curse of dimensionality. So the more features you get, potentially the more pain you're going to experience. That's not to say that you might get rid of things. That's why we do feature selection, to determine what things actually contribute the most to the outcome. But the basic idea is you want it to be as simple as possible, but yet not sacrifice the fidelity of the model such that it becomes a problem. So it's kind of Occam's razor to some extent, is the way to think about it. And you want to make sure that whenever you're finding your data sets, you let them kind of guide what you do. Don't start with the algorithm. Start with the data. Figure out what seems like it might do well, and then likely you'll want to do some stuff like AutoML. And I'll probably show that in a moment. Let me pop over and spin up a cluster. I'd rather try to get it to start running now rather than be waiting on it after we finish looking at K-fold in Keras. Sorry for the pause. Almost there. So what I'm doing is opening up a Databricks workspace. And I'll kick off, assuming it gets in pretty quickly, a cluster. Make this bigger. I'll go ahead and start up an ML. This is an ML runtime. It's not a real big cluster, three workers, so a total of 4 nodes. Hopefully it'll start up. While it's doing that, we'll come back over here and take a look at Keras. So this work is taken from this blog post, and the basic idea is to talk about doing classification on Keras with various approaches, or on Iris with various approaches using Keras. So we're doing a classification. We're dealing with our good friend the Iris dataset, which we spent a fair amount of time looking at, and then we're going to take a look and see how we can train with it and do some cross validation with K-fold. So go ahead and step through it. So the data set you're all familiar with. At this point, you're probably sick of looking at flowers. I'll go ahead and download it from a GitHub repository of my own. and show basically the different pair plots, and to see the ways that you can potentially separate them and by what pairs of things do pretty well. And the interesting one that kind of draws your eye is these in the middle seem like you might actually have a chance of splitting them if you consider petal length by sepal length. That seems to be, and possibly over on the right, in the middle on the right, that may also be. But anyway, so we take a look at the columns. What do we have? And these are nothing terribly new. Our typical data that we've seen a bunch of times, and then do the typical sort of splitting your data frame into two different data frames, one of which is your targets, the other are the features that are going to be used to try to get to that target. They're simply parallel arrays, for lack of a better word, so the rows line up. And then, so there we see the targets, here we see the features that might get us there. The one-hot encoder I think we've talked about before as well. It's a way of essentially turning essentially categorical sort of things into a vector of bytes or bits. So the basic idea is that you essentially turn something into a 1 or a 0 and a series of those to fit the values. And so we can see here the various representations having turned our y into a vector of essentially an array of 3 items for each one of the records with the various things being on. And this is basically because neural networks don't really like strings. They prefer numbers. And it's just a way of doing that mapping between the two so that you can easily get up and running. So next we're going to do 5 folds in our k-fold approach. So k is equal to 5. And go ahead and split it. No sort of seeding of the random number generator, so this will be reasonably random, so you can get a sense of how it is going to be doing it. Create a model using, or a function that's going to return a model. In this case, the cross-validation model is sequential. And then, so we take a look at the hidden layers, 3 neurons. So this is going to be the structure of the model. So that's what we're creating up here. So this is reading it. It's a relatively simple sort of neural network. You've got one hidden layer, so it's not a deep neural network by any stretch. There's 4 inputs, which corresponds roughly close to our it's close to our well, it's our features, right? And then you've got essentially 3 outputs, right, that with a softmax activation function. And then we're basically going to compile it, and then we're taking another look at our x inputs, making sure everything is an integer, and turning it from essentially a record, so to speak, to a vector or an array. This is an array of arrays. We're going to run for 50 epochs, and basically what it's doing is going through and doing this split for each one of the x and y's. So our one hot encoded vector, and then the features that correspond to it. We're getting the model. We're basically training the model, getting the history, and then starting to keep track of how we're doing on each one of the folds as we go through. And we're up to the 4th fold. And testing accuracy is doing very well on certainly some of the folds. And the training accuracy is in the mid-90s pretty much across the board. And we are keeping track of the accuracy by essentially appending some items here. And here we plot the performance over the number of epochs. So we did run for, again, 50 epochs, which passing in here, and we did that 50 epochs 5 different times with 5 different folds, and so that we can basically see the training score and the cross validation score in based upon the number of epochs. And the way that it should work is pretty much what you're seeing. It should start flattening out. There's a point where it's essentially diminishing returns. The more that you run it, the longer, the more likely you are that you're overfitting, and also you're potentially not getting as much of an improvement. And that's kind of one of those times when you know to stop, is when things start flattening out. And if you, because it is moderately fast, one way to try to see if you can improve the accuracy is to increase the number of epochs. So let's take that out to 100 and let it run. It does take longer, obviously, for each one of the epochs, because, or each one of the folds, because it is a lot more work that it's having to do. But you can also see that the training accuracy thus far is pretty good. So 97.5. We gained roughly 3%, but then we're also seeing now some instances where it's much worse. So likely what we'll find is that when we plot it, it looks pretty good, and then it flattens out, and then it may actually, it's possible to start going down. But you can see here that it definitely is flattening off. It's approaching something, and realistically, there's not much point in going beyond 50 epochs. It's not going to necessarily do a whole lot of good. And in fact, it could do some harm. So with that, we've talked about using K-fold on a real-world data set, and so on. Jumping back to talk about Deliverable 6. Doesn't look like I'll probably have time to get to AutoML. I'll probably talk about that in a future discussion, because it's cool stuff. I think we've actually talked about it before. So your competency for Deliverable 6 is to, you guessed it, apply cross-learning methods, so cross-validation, as a means of validating your models. You're the chief data scientist for Reliable Dynamics Inc., RDI, a robotics development and manufacturing company. You need to ensure that the company's various lines of robots operate consistently given a standard set of test data. You determined that the best way to validate any given operation is to use the cross-learning method. High-quality products that operate safely is what has given your company a competitive edge, and it wants to stay ahead in the robotics market. So in order to uphold your company's high standards, you need to validate that every robot that leaves the RDI plant has passed critical diagnostic testing. You need to ensure that every robot is consistent in identifying similar patterns from a wide variety of test data. To do this, you must explain and utilize model validation in an example of your own choosing. Explain the cross-learning method. Use Python to apply cross-learning methods into real data sets. Your report should be in the form of a Word document containing screenshots from Python where appropriate. So use screenshots of Python as a means of explaining things that you're wanting to demonstrate. The rubric, the criteria 1, a thorough and detailed discussion has been developed on the utilization of model validation, and it's present, and it's well developed, and accurate examples are present as well. A thorough and detailed discussion has been developed that explains cross-learning And it's also, well developed and has accurate examples. A thorough and detailed discussion has been developed on the application of the cross-learning methods into real data sets. And a thorough and detailed discussion has been developed on the application of cross-learning methods into real deep data sets through the use of Python. So having some examples of how you actually do it. Again, scikit-learn's test, train, split method is your friend. Deliverable 7 centers on sort of the whole pulling things together. So explain an artificial neural network, design a neural networking algorithm using the observational data training process. That's also a labeled data set. Apply deep learning methods for classification of data sets. Apply support vector machines, SVM, for classification of data sets. Apply genetic programming and genetic algorithms in handling large data sets. Apply cross-learning methods for validation in the modeling process. So you're working now at Big Heads Inc., BHI. It's a universal think tank that offers its services to all companies in the world. BHI is known for its out-of-the-box solutions that have saved or generated large sums of money for its clientele. Its services are not cheap, but its customers have reaped much more than they have sowed. As chief in the machine learning department, you have been tasked to develop a white paper, also known as a technical document, which delves into all aspects involved in planning, designing, building, and operating and evaluating machine learning models. Your white paper will be used as the foundation for future company to client interactions that encompass machine learning. So your instructions, in order to have a well-balanced artifact, you will synthesize the various concept components and methodologies listed below that address machine learning. The results of your work will be in the form of a white paper created in Word and include screenshots from Python where appropriate. Your white paper needs to have a thoughtful flow, be comprehensive, and follow APA standards. So try to keep it in APA format. I strongly suggest the use of an APA template. It makes your life much easier. Evaluate concepts of neurons, nodes, and layers, and appraise how artificial neural networks work and learn. Explain the backpropagation process and gradient descent. Assess the typical results of each step in a neural network and describe the nature of training and test datasets. Explain how convolutional neural networks, CNNs, provide robots with eyesight, the ability to detect and recognize things. Use Python to design an appropriate number of layers and nodes for real datasets and apply deep neural networks to the grasping dataset found in the resources section. You don't actually have to do that because it is relatively complex, so skip over the grasping dataset. Interpret your results of this deep neural network. Explain support vector machines, SVM, and apply them in practice using Python. Explain the use of kernel regulation gamma and margin tuning parameters of SVM. Produce examples of genetic algorithms and genetic programs. Use Python to design and implement an appropriate data structure using a genetic program to implement a problem of your own choosing. And then determine an appropriate performance function for a real-world problem. And then use Python to validate your model and explain the cross-learning method and apply cross-learning method into a data set of your own choosing. Your rubric, quite a few criteria here. A thorough and detailed evaluation and assessment has been developed that explains the concept of neurons, nodes, and layers and assesses typical results of each step in neural networks as well, and it's well developed and accurate examples are included. A thorough and detailed explanation of backpropagation process, gradient descent, and convolutional neural networks. A thorough and detailed explanation of support vector machines, SVMs, the use of kernels, regulation gamma, and margin tuning parameters, and then a thorough and detailed use of Python has been used to design and implement an appropriate data structure along with a utilization model validation that explains cross-learning methods is present as well. A thorough and detailed example of genetic algorithms and genetic programs is present. and a thorough and detailed determination of an appropriate performance function for use in a genetic algorithm for a real world problem is present and well developed and has accurate examples. So, what I would strongly suggest is merging together and doing a little editing of all the stuff you've done throughout the course. It does build on it, it does tie it together. This need not be totally new work. It's more about editing, turning it into a single artifact versus going out and doing a whole bunch of work that's likely going to be quite extensive to do. So with that, I have reached the end of our discussion of Unit 6 and deliverables 6 and 7. I will be likely circling back and going through some of the original or earlier content of units to help you guys get going. As always, if you have any questions, let me know. That's what I'm here for. As always, stay safe, and we'll talk again soon.